but I sometimes go by Michael. And my project is gonna be on rare earths, high temperature ceramic materials. I know it's a little bit different than the polymer derived ceramics, but it's still a pretty interesting topic. First, we're gonna start with a little bit of an introduction. I mostly work on the first column transition metals, mostly just concerning scandium, yttrium, and the lanthanides. Currently, I'm mostly just focusing on yttrium-based ceramics. And these are of interest because of their use in batteries, lighting, aerospace, and some nuclear containment applications. Although due to the refractory nature, their thermodynamic landscape is very difficult to determine. Some other material properties that are very important to include are, of course, their high melting points, their low vapor pressures, their resistance to decomposition, whether it be by temperature, pressure, or chemical attack, and of course, chemical inertness. Extensive research have gone into earth materials that have to do with carbides and nitrides. Carbide, I'm sure you guys know, they're very good structural materials and wear resistant. They have high hardness, and then they're pretty awesome. And for the nitrates, they're mostly used in electronic applications. In the other hand, the ones that I'm focusing on are mostly just oxycarbides and oxynitrides. Those that have not been researched a lot. They're being neglected, basically. And they're, regardless of their usefulness in some industrial applications that I'll be talking in a little bit, most of the information in these materials is single source and is non-current, so it's very limited. And that's why it's really important for us to expand on this data. Some of the important examples of some of the research that's been done already is just on their crystal structure for like carbides and nitrides, of course, electronic, magnetic transport, and the thermodynamic properties, and of course, mechanical properties. As we know, all these properties are very, very, very intertwined and have to do a lot with the structure and phase transformations, and that's why they're very important to study. Now I'm going to talk about a little bit of an application that I thought was very interesting of these materials, and it's just carbide-based ultra high temperature ceramics. Like many people here in previous presentations have talked about the specific application. And the most common thermal low conductivity coating that is used right now in space engines is the zirconia. Is zirconia partially stabilized with yttria, or also denominated 7YSC? And it has some advantages and some disadvantages. Like the most important advantages of this material, it's its porosity and the nanostructural defects that allow for a acceptable thermal strain tolerance, as well as low thermal conductivity. This composition range also allows for the ferroelectric toughening to be active, which means it's very mechanically robust, and hence it's very useful. And this boosted the maximum working temperature of turbines. But in more recent years, they've wanted to increase the operating temperature of these turbines to, I want to say, greater than 1,500 degrees Celsius, which is pretty high, right? And this material specifically loses the phase stability and strain resistance around or above 1,300 degrees C. Its thermal conductivity is not low enough to operating at these high temperatures. So that's why, you have to research other materials. And after 1,200 degrees Celsius, environmental silicates melt and deposit on the surface of the coating, which might cause them to, fail prematurely, which brings us kind of to the importance of this research project, which is crucial because most rare earth containing materials don't have well-studied phase transitions below their melting points. Like I said, their melting points are like close to around 2,000 degrees C, and equipment, it needs to be specialized in order to actually get these thermal information, most of the research on this, like as I said before, it comes from a single research laboratory in Orleans, France, and they made their, they did their they took out their articles around the 60s and the 70s. These measurements, along with other experimental studies, are the ones that compose the foundation for most of the computational phase calculations that are out there currently, which is also part of my project, right? It's a little bit of experimental, a little bit of computational stuff. So these calculations need refinement and more experimental data to produce superior theoretical thermodynamic diagrams for more complex systems. As I said, the fact that most thermodynamic calculations are based on low temperature materials doesn't really fit well with the high temperature polymorphism and stuff like that. So now I'm gonna talk a little bit in more detail on my specific project, which, like I said, it's dealing with yttrium and yttrium oxycarbide, the FCC phase, and a little bit of the computational methods, not a lot. So the first thing what we're gonna talk about is the thermal analyzer instrument that I'm using currently to synthesize these samples. It's called a SET624. It runs up to 2,400 degrees Celsius, which is very good. And like I said, I'm currently only using it for synthesis, but it is a thermogravimetric instrument as well as a thermal differential analysis instrument. So it can do both, but we haven't really been, or I haven't really been using those functions in the instrument. The other part, of course, is going to be the computational part, which is mostly just, it deals with initial density functional theory with higher functionals. And that's like a partnership we have with the van der Waals group, who develops the tools to calculate these, the thermodynamics of these rare earth systems. And now, like, we're gonna move on to my experimental overview, which just have to deal with like the previous research articles that I used to develop my current experimental protocols, which have to do with the, well, so first, the first article is was written by Holcomb and Carpenter, which deals with the carbothermal reduction of yttria with graphite in order to get the yttrium oxycarbide phase, as well as some aspects of the Brose, Karen, and Hajek. I didn't really use them that much because they changed their reactants, and we will move on to trying those later on in the future. For the Holcomb and Carpenter, they used a 1-to-1 molar ratio of yttria to graphite powder under vacuum for around 50 hours, which is a very long time, and at around 1,500 degrees Celsius. For Brostek and Hajek, like I said, they kind of ran similar reaction, but with different reactants. They did same under vacuum for 43 hours at a higher temperature of 1,600 degrees Celsius. They also used yttria, but changed it to granular carbon in different ratios by weight. And they actually used yttrium metal as well. So it was like a mixture between yttrium metal and yttria. And their results produced around 30% of yttrium oxycarbide phase. The other 70% is mostly yttrium carbide and derivatives of yttrium and carbon and oxygen. But that's the one that we care about right now. And in Holcomb and Carpenter, they actually ran their synthesis in a thermal analyzer like I did, and that's how they got the characteristic mass loss of around 9.2%. So now I'm going to talk about the one that I developed based on these on these articles, which is the same 1-to-1 ratio, but I used by weight because I was trying to just to get acquainted with the instrument and just kind of develop the protocol before I actually did the by mole, which uses a lot of yttria. But yeah, so I mostly just did 1 gram samples because the thermal analyzer only fits like 50 to 70 milligrams. I sometimes did less than that, sometimes did more than that, but it's very hard because it's just like, it's too little. So I mixed the samples using a mortar and I palletized them using a pallet die press. I don't know if you guys know what a pallet die press, but maybe I should have added a picture or something. The SET624 reaction time was over 15 hours in the argon atmosphere at 16 well, sorry, 1,630. We couldn't extend the time because the instrument has limitations on the time. So in the future, we're planning on using a furnace to extend the time. And then the preliminary data acquisition was done in a Bruker 2D XRD within 15 minutes of the synthesis end time, because this material is moisture sensitive and it tends to decompose back into yttria after a while, like if it spends too much time out in the moisture and whatnot. And that's why we kind of employ glove boxes and desiccators. So in the preliminary results, the XRD measurements showed that there was no reaction between the E3 and the graphite powder. And also there seemed to be different weight percentages in the scattering data. I will show in the later slides. I just wanted to put the conclusion first. The results could be due to lower purity samples, much shorter reaction time, and the decomposition of the moisture-sensitive materials during the sample transfer and XRD measurements. Again, the lab right now sits pretty far from the XRD room, so I have to like kind of transfer it out. We kind of offset the time it takes just by using a vacuum sealed container before I, transfer it. There was also a mass loss of about 8.6 milligrams or 17% during the Celsius reaction, which is about double what we should be looking at. And based on discussions that I had with, some of my people in the group, they figured that it was based on the fact that there are impurities in the yttria powder that need to be taken care of first. So it needs to be dried and those need to be getting rid of before we actually do the reaction. It also upsets the 1-to-1 ratio based on the decomposition of those impurities. Here is the XRD data for the original sample that I ran in the XRD. As I said, if you can see that little one in the corner, it's a basic yttria scattering data spectrum, and well, it fits well with what we can see here, except for the biggest peak, that's graphite. And here, like again, like you can't really see that, but it's a weight percent of 75 to 25%. Mostly just graphite, which means like again, like there's a lot of graphite over yttria, which might have contributed to the fact that there wasn't a reaction. Here is the one afterwards, and I added the graphite XRD spectrum so you could see kind of like where the peak is supposed to be. And here we have a 95 to 5% difference, which led us to a conclusion that we need to develop better mixing methods for our powder. We're still kind of in the discussion to see what we can do about that. So in conclusion, what we need to do is to increase the ratio of yttria to graphite on the sample or the procedure, so that we can get a higher percentage of the yttria marks the carbide phase. Develop better mixing methods to raise the homogeneity level of the graphite to yttria samples. Again, I did mortar, so it's kind of like just 10 minutes of just like giving a good mix, and I thought it was okay, but I think it's gonna have to be further studied. Stretch the time of synthesis closer to 4350 hours to follow more closely the previous studies. Again, I only ran for 16 hours, and I'm sure that is not enough time for it to actually react. Try the original yttria sample to obtain the more accurate weight loss measurement and ratios. Again, I used a weight ratio, so I'm gonna do molar next time, and I'm gonna try and dry the yttria. Now that we had some problems with our dry boxes, so it was kind of hard to work in non-moisture sensitive environments. And then finally swap the synthesis reactants from pure yttria to a mixture of yttrium metal to yttria. Yttrium metal is more reactive. It's also very moisture sensitive. So again, we needed to develop, better lab facilities in order to work on this stuff. And finally, of course, start working on the computational calculations with Dr. Qui-Jun Hong. He's a new faculty in ASU from the Van der Waal group. This coming fall, we did like do a couple of preliminary calculations, but I chose not to put them in the presentation just because I need further analysis, and it's a good comparison to the experimental data, and yeah. And yeah, that's it for my presentation. Thank you for inviting me. Any questions?